Hi, in this video I'm going to introduce the concept of a vector space. So a vector space, which is sometimes known as a linear space, is a non-empty set of objects which we happen to call vectors, but they don't have to be vectors, which we can add and multiply by a scalar. So it's simple as that. Now, if V is a vector space and we have any objects U and V which are members of V, or U and little v are members of V, and we have any scalars, which is alpha and beta, which is a member of F. Now F is a field. A field is simply a set of all objects for which a binary operation exists. For now, just think of F as being a set of real numbers. Okay, so alpha and beta, if you think of those as real numbers for now, and U and V are just objects. And if these 8 what we call axioms are satisfied, so 4 of them, A1 to A4, deal with addition, and M1 and M4 deal with scalar multiplication. So if these axioms are satisfied on any two vectors, U and V, in our space V, then V is known as a vector space. Now, I mentioned before, but we call those objects vectors, but they don't have to be vectors. So these vector spaces originated with study of vectors, but it also applies to other mathematical objects. So, for example, your U and V could be matrices, they could be functions, any mathematical object. Let's take an example. The set of real numbers is a vector space, because if you take any numbers U, V, W, okay, in the set of real numbers, and if you have a look at all of these, you can see that they're all satisfied. So the set of real numbers is an example of a vector space. If we were to take the positive real numbers, okay, so that's any real number greater than 0, this is not a vector space because it doesn't satisfy all of these. So for example, 0 isn't a member of R+, so that A3 is not satisfied. So there doesn't exist a additive identity element. If we look at A4, also that's not satisfied. Okay, so it has to be a vector space. All of these axioms need to be satisfied.